You know how you can smell a barbecue from like clear across the park, but you have to stick your nose right into a cold salad to smell anything? Or what about this one? Why do ice cubes float in your drink? It seems kind of weird, right? Well, these aren't just random things. They're actually clues to this hidden world that makes everything around us work. So today, let's go on a little journey and uncover the secret life of particles.
Okay, so let's kick things off with a few of these everyday puzzles. I'm talking about stuff you've probably seen a million times, but maybe never really thought about why it happens. But trust me, the answers all point to this amazing, invisible world.
All right, first puzzle. Imagine it's a hot day and someone's grilling burgers. You can smell that amazing sizzle from way across the yard, right? Now compare that to, say, a cold salad you pull out of the fridge. You pretty much have to have your face in the bowl to smell it. So what's going on there? We're going to circle back to this one, so keep it in mind.
Okay, here's another one for you. Think about it. Most things, when they turn from a liquid to a solid, they get denser, they shrink a little, and they sink. But water? Nope. Water does the opposite. Ice floats. And honestly, it's a really good thing it does. If it didn't, lakes and oceans would freeze solid from the bottom up. So what makes water the exception? Well, it all has to do with how its particles arrange themselves into this special crystal structure when they freeze, which actually makes ice less dense than water.
And for our last puzzle, let's talk about that instant cold feeling. You know what I mean, when you're sweating after a run, or maybe when you spill a little nail polish remover on your hand. That sudden chill, it's the same basic thing happening. So what on earth connects sizzling food, floating ice, and a cold, wet palm? Let's dive in and figure it out.
All right, the answer to all of these questions, it all comes down to one thing: matter. You know, the stuff that makes up literally everything in the universe. And to really get it, we've got to meet the tiny, invisible particles that it's all made of.
The official definition is pretty simple, right? If it takes up space and has mass, it's matter. So the chair you're sitting on, the coffee in your mug, even the air you're breathing, it's all matter. It's all just a giant collection of these unbelievably tiny particles.
And these little guys, they live by 3 basic rules. Rule number 1, there are always spaces between them. Rule 2, they are never still. They are constantly moving, jiggling, vibrating. And rule 3, they attract each other, kind of like tiny magnets. Seriously, these 3 rules, they're the key to understanding, well, pretty much everything.
So depending on how those 3 rules are working, we get the 3 states of matter we all know and love: solid, liquid, and gas.
And that's really it. It just comes down to how the particles are arranged and how much they're moving. That's the only difference between a solid block of ice, a glass of water, and a cloud of steam. Just the particle arrangement.
Okay, this chart lays it all out perfectly. Let's look at solids first. The particles are packed together super tight in a neat, orderly way. The attraction between them is really strong, so all they can do is just kind of vibrate in place. That's why a solid has a definite shape, right? Now for liquids, the particles are a bit looser. They have more energy, so they can slide and tumble past each other. That's why a liquid flows and takes the shape of whatever you pour it into. And then you have gases. Man, their particles are just going wild. They're full of energy, zipping around all over the place with barely any attraction to each other, which is why a gas will expand to fill any container you put it in.
So if the only thing separating a solid from a liquid or a gas is just energy and how the particles are arranged, then it totally makes sense that we can change them from one state to another, right? Let's take a look at how that happens.
This diagram pretty much shows the whole story. It's all about heat and pressure. Think of heat as energy. When you add heat, you're giving the particles more energy, making them move around more. And if you take heat away, cool things down, you're doing the exact opposite.
So let's talk about melting. You take a solid, like an ice cube, and you start heating it up. Its little particles start vibrating more and more frantically until, bam, they break free from that rigid structure. And that's melting. But here's a really cool part. While the ice is melting, the temperature of the water doesn't actually go up. It stays at a frosty 0 degrees Celsius. All that heat energy is being used to break the bonds between the particles, not to raise the temperature. Kind of weird, right?
All right, so what happens if you keep adding heat? Well, you crank up the energy of those liquid particles even more. They start moving faster and faster until they hit the boiling point. At that stage, they have so much energy that they can completely break free from their neighbors and just fly off as a gas. And that, my friends, is vaporization. And then there's this really cool exception, this little shortcut called sublimation. This is where some solids, a great example is dry ice, can just skip the whole liquid phase entirely. They get enough energy to go straight from a solid, poof, into a gas. It looks like they're just vanishing into thin air.
Okay, now let's zoom in on one of these processes in particular, because this one is the key to solving those puzzles from the beginning. We're talking about evaporation. It's kind of like boiling's quieter cousin, and it's happening constantly, all around us.
So here's the absolute most important thing to get. For a particle in a liquid to escape and turn into a gas, it needs a burst of energy. And where does it get that energy? It steals it. It literally robs heat energy from whatever it's touching from its surroundings. So when that particle leaves, it takes that heat with it. And that's why evaporation makes things colder. This is the big secret. This explains so much.
Want a perfect example? Think about pouring hot coffee or tea into a saucer to cool it down. Why does that work so well? Well, evaporation only happens on the surface of a liquid. A saucer gives the liquid a much bigger surface area than a cup, so way more particles can escape at the same time. More particles escaping means heat is carried away much, much faster.
And this is the exact same principle behind those old-school earthen pots, or matkas, that keep water so cool. The clay pot has all these tiny microscopic pores. A little bit of water seeps through to the outside surface, and then it evaporates. This constant evaporation is always pulling heat out of the pot and away from the water inside. It's basically nature's air conditioner.
So, it turns out there are 4 main things that affect how fast evaporation happens. First, surface area. We saw that with the saucer. More surface means faster evaporation. Second, temperature. Hotter temps mean more energy, so particles escape easier. Third is humidity. If the air is already full of water, it's harder for more to evaporate, so lower humidity is better. And finally, wind speed. Wind whisks the evaporated particles away, making room for more to escape. And when you put all that together, you get the perfect explanation for why those swamp coolers work so well on a hot, dry, windy day.
And that brings us right back to our very first puzzle, the sizzling food. Because hot food has a much higher temperature, those little aroma particles are just bursting with kinetic energy. That's the energy of motion. They escape into the air way more easily, and they travel faster and farther, which is how they make it all the way to your nose from across the yard. The particles from cold food, they just don't have the juice to make that long journey.
So there you have it. From the smell of a barbecue to the chill you feel from sweat, it really all comes down to this secret life of particles. Which kind of leaves us with one last thing to think about. If even the particles in the most solid-looking thing you can imagine, like the desk or table in front of you, are constantly vibrating and moving, is anything in the entire universe ever truly, completely still? Something to chew on.